that we are going to talk about the non-structural damage today. This is actually based on one thesis that was done in 2019 by one student from Philippines, and she did a lot of work. And after that, we developed an app based on her work, which we hope to reactivate. Okay, so this is, I don't know if you have shown, I've shown you this slide or not, because I normally used to show. This is the scene from a movie called The Towering Inferno. And it's a very old movie, 1977 or something. And it's a very interesting movie. You can go and find this clip somewhere on YouTube. And in that, what happens is that they show that the building catches fire. And it's, remember, it's before computers a lot, and the building is burning and the people are trapped there. And then they show that outside the burning building, a structural engineer is sitting on a desk with his calculations. And the fire chief, Steve McQueen, he comes and asks him, how long do you think the building will survive this fire? Because I need to send people to rescue. And the structural engineer does some calculation and say 2 hours. I can assure you that even with all our simulation, all our software, all our modeling, we cannot answer that question, how long the building will survive before it fails. But the people expect that kind of answer from us. Exactly the same thing. People expect engineers to be able to tell them about safety in their view, not in our view of the code, factor of safety and all that stuff. So this is a reminder that even long time ago, they expected engineers to answer that, which we still cannot answer. In fact, that prompted me to do some research on trying to just figure out how long a column will last in a fire. And then we did some finite element modeling of and then heat transfer from the outside through the concrete to the rebar, and then do the fiber modeling and do the nonlinear analysis of the section over time, over temperature, try to see when the rebars will yield and when the concrete will crush, including temperature effects, right? And just for one column section, it was very hard, let alone the whole building. So we still are very far from really simulating the damage in that way. So now, we have seen this before. You've seen many of these slides that a lot of progress has been made, but still the progress is not as people expect from other products. Like, for example, you buy something, it doesn't work, you return, you get your money back. The structure doesn't work, you cannot get your money back. We don't have that kind of warranties yet because we just don't do enough yet. It's not a product yet, right? So we are still very far from what other people expect from other things. So let's just move forward. We are mostly concerned about that. Safety is our prime concern. That's where we draw our line, that our job is that. And once we do that, we think the rest is somebody else's problem. But that is not how the public sees, and that's not how the society's damage is happening. The cities come down to a halt, not because structures fall down, because there's a damage or a perception of a damage or perception of unsafety. So that's what we are kind of talking about today. So factor of safety, as I mentioned, we have all these formulas to deal with that. But once again, it's all about safety and factor of safety. And factor of safety is so unreliable way to look at the things, because the way it is calculated, the way it is assigned, it doesn't give us any real knowledge. It hides everything in that factor. All the things that we should know, we don't know, we call it factor of safety, which is the factor of ignorance, you may call it. So if we want to remove all of that, we really need to understand, in depth. So that is the area that we don't know. We put it in the factor of safety from 0.5 FY to yielding and beyond. We just don't know anything, what is happening to the structure and what is happening to the things attached to the structure. We just draw the factor of safety. This is the working stress method where we started. And then we now go a little bit up to FY, but we still don't know. So now you remember this theory that we developed. We go to all the way to FY, and then the moment curvature curve and all, we did that. We can go a little bit beyond that. But this is the level of design, right? So we are still talking about that level. And after that, we close our eyes and we already factor the loads, and the loads are not factored and they're real. all of those things. So many things you have seen, we talked about this curve quite a bit, but now you start to understand the importance of this curve. Because now we are talking about ductile limit and strength loss and residual strength and ultimate strength. So this building that collapsed in normal circumstances, even for the most credible earthquake, MCE, the structure is supposed to go to that residual strength and stay there. It is never supposed to come down to zero capacity, right? No matter what happens. But this structure somehow went straight to that point. Okay? So that's still something that but the point that I'm trying to make is that we need to have this damage thing and we need to stay away from that. But even after that, we have the strength loss, we still need to have residual strength. So residual strength for structural elements and non-structural element is different. The problem is that the non-structural elements, the residual strength is very little because it's brittle. And so as soon as they reach, they're just gone and their connections are gone. And so the problem is that we don't design them to absorb the movements, acceleration, and velocity. There are three components: drift, displacement, velocity, and acceleration. And things get damaged differently from these three things. Some things get damaged by drift, something gets damaged by velocity, some things get damaged by acceleration. So we have to separate the non-structural component damage to these three categories. So seismic design approaches, we have already talked a lot about, I'm just summarizing. So the earthquake, we need to talk about the drift, we need to talk about the acceleration and ductility, levels of damage, life safety, collapse prevention, energy, damping, and many things. And at this point, what is less important is stress, strain, strength, and stiffness and factor of safety. So those become almost irrelevant in this discussion because we are trying to, as I mentioned in my other class also, that earthquake is bringing the level down, not up. Wind is service level is here. We multiply it to bring it to the design level. Earthquake is already very far above. We are dividing it to bring it to the design level. And that division has so many issues. And that's why we cannot assess these things accurately. And we need to, we should expect that the real force may be much higher than the design. And that's why all this damage actually can happen. So this is the image from Nepal. I went there. This actually presentation was made after that earthquake. And this is a very interesting case study because there were three buildings there, three towers of different height. And when you go to the site, you can see that there's a lot of damage very clearly. This building was designed very well by good consultants in India, following the codes, but look what happened, right? It's a non-structural damage. Structure is still safe, but do you think anybody will live there? You will not live there, right? So even if we do PBD, we will still get this. That's the sad part. That even if we had done performance-based design for that building, we would have still gotten many of those cracks. So even if we do nonlinear analysis, because we are expecting the walls to break, you model the walls in the nonlinear models. In fact, they did not model the walls, but now we recommend everyone to model the walls by using strut models. But the strut is designed to break, which means we are expecting that the walls will break. So it's a perfect structural model with the damage, but it is completely unacceptable to anybody, right? And people spend a lot of money to earn from abroad, bring it back, buy something, and then building is gone, right? So this is a major problem, that this kind of damage, which is acceptable by us as a design process and acceptable by the codes and even acceptable by the PBD, is not acceptable by the public. So this is what we are talking about today. And that is what we talked about, all the steps, all the way to resilience. So now we are talking about consequence and resilience beyond PBD. So code-based design, we have talked about, I can skip this because it's a repetition. mostly code-based design basically want safety, that the structure safety, but never checking of course, serviceability is checked, but it's a much smaller earthquake, right? But as soon as it goes beyond, we expect the damage to come, but people do not expect the damage to come. That is the key. So this is the historical approach, that we put a cloud in this area above that. After linear, we have kind of a unknown zone. We just don't know what is going to happen, and we keep that way until PBD came and we start to explore a little bit more. But still, a lot of things are in the cloud. We still didn't check a lot of things that I mentioned to you there. And then because we have the elastic response reduced by R is wrong, and so many things. So codes try to remove that cloud by putting this one, but then add a more cloud, because R itself is not reliable. So now you can see that there are so many codes. And this brings us to another question, which is very simple question. Which code is right? Just the fact that three codes differ prove that none of them can be right. Right? It's as simple as that. Because the structure is the same, earthquake is the same. Why two codes are telling us that one is saying it's safe, one is saying it's not safe. One is passing, one is not passing. So which means this is quite arbitrary. All the codes are rather arbitrary. And that's why we did one thesis a few years ago. We said, okay, design the same building with nonlinear analysis, and first design them to 3 different codes, and then do nonlinear evaluation to see which code predicted the best, was close to the PBD or gave the best performance. So we checked ACI, we checked BS, and we checked Eurocodes, right? So we found that different codes are close in different ways. Some codes predict something better, some codes predict something, but overall, we found that the Eurocodes were better in many ways. So they were able to design a structure which performed better than the structure designed under other codes, right? So it's just, but it's not a statement. It's just maybe for that building, it happened to be like that, or that zone, it happened to be like that. But we just did, 3-4 cases, not much. But the point is that they all give us different design and different performance. So that's the other issue here. So if they differ, can all of them be correct? Logic says no. If there's only one truth, then all of them are giving different results. So chances are that none of them are. So the other thing is that, did we inform the structure to follow a certain code? You design based on a code. Did you say, no, I'm designing you ACI, please follow the ACI when the earthquake comes? Of course not. It's going to perform the way it likes to perform. It has to perform. That's why PBD is not code-based, right? Because we want to see real earthquake, real structure, and let them decide. And then another one, code changes every 3-4 years. Formulas change, limits change. Should we go back and fix every building? Cannot, right? So which means a building which is passing today, next version, same building is not passing. What is that, right? But of course, that's how the progress is made. But the point being that we should not take these things extremely seriously and recognize that they have limits. Okay, so this is all we've talked about that. Let me just move on to the topic today, because PBD we've covered quite a bit. So this performance point is the key that now we are looking for, that we are trying to say, okay, let there be a real earthquake, let it go down as the structure deforms, and let the performance be there, and let them meet at a point, and find out that point where the reduced demand and the actual nonlinear response of the structure meet, and then we decide whether that point is acceptable or not, and link that point to everything. That's the idea, because we know the drift, we know the displacement, we know the damage at that point in the structure. So now we can, for different earthquakes, we can create different performance points. Low earthquake over there, high earthquake, very high earthquake, some earthquake beyond that. So we can find out multiple performance points for different levels of earthquake, and then see how the structures, response will be. So that brings us to this one: operational, intermediate, life safety, collapse. So we can say, okay, for this earthquake, we want the structure to be like that. For that earthquake, we want it to be like that. For that earthquake, or this building, for this earthquake here. So we can decide now two things: same building at multiple different earthquakes, and different buildings for the same earthquake. For example, hospital, we will say, okay, even though earthquake is very strong, I want a hospital to be operational, right? This is storage, no, but there's nothing important there. Okay, fine, we just prevent this one. So for the same earthquake, different buildings can have different performance expectation, and same building can have different performance expectation for different earthquake. And this gives us a complete freedom to evaluate everything, right? So that's what the PBD is, what we have been talking about. And we can put it on that curve, as you can see from here, so we can link everything together. Next, this is the main slide. Because once we have that, we can then connect not only damage, we can also put casualties, human loss, life, and serious danger, downtime for rehabilitation. Very, very important. How long you have to shut down the building to repair it. It's a hotel, it's a restaurant, they lose business for 1 day, 1 month. That loss is huge. For a critical operation, it's much, much bigger than the cost of the building, maybe. And the cost to get it back, right? And then retrofit cost to minimize consequences. So everything we can put now on one sheet. Once we have done the performance evaluation, we go beyond. We don't stop at just performance. We go to these 5, 6 different new lines also and start to evaluate them. And then we get the total resilience of the structure. That means can say, okay, and then client can decide, or authorities can decide that, okay, we don't want it to remain shut down for more than 1 month. But do we have the tools to do that? Do we have that? And luckily we have. We can actually go to the level and say, okay, you want this to be repaired within 1 month? We can do that. But the problem is not about that. I will tell you what the real problem comes later. So performance-based design, we talked about that we need to involve all these people now to make sure that everybody works together. So we need to involve the architect, first of all, because non-structural damage will be linked to them, and then structural engineers, the performance-based design people, the site-specific consultants, and the PBD reviewers. Everyone has to agree that this is what we are going to do, okay? Because this is not the code. So client, architect, the designer, structural designer, the PBD reviewer, and the PBD consultant, everyone has to agree this is the performance of the building that we want. This is non-structural, structural damage, everything that we want, it should be like that. So that has to be agreed, because then all that next will depend on what is agreed. Okay, first of all, first is here number 1. Everyone has to agree that we are going to go beyond the codes. Okay. Now you can ask a question, do the codes allow that? And the answer is yes. Codes actually say that if you can prove that what you're saying is better than code, you can go ahead. And if somebody can certify that, right? So by definition, procedures like this are allowed by the code, but you have to qualify to get that. So that's number 1. Then we need to have sophisticated structural modeling. That's what we are talking about. More than what we did for the class project. A lot more than that. Okay? And some groups are trying to do that, fine. But we need to learn, and we have a few webinars. You have seen Dr. Pramin present a lot of the details for the nonlinear modeling. So we need to have that ability. And then software, state-of-the-art software to actually do. There aren't many programs that do this well. Perform 3D is one of the best. As you know, ETABS is there now, but not many other people. So many other programs are there. Myra, so many people are there. Many softwares are falling behind. They haven't caught up to this properly. Perform is the leader, gold standard. And then, of course, ETABS and other SAP are also coming up. So you need to have software. You need to have the ability to model that, and you have to have people who agree to do this one. Linear, nonlinear, result, and interpretation. This each block is like color is changing. It's like one order more difficult than the other one. The first gray block is easy. Everyone can do that. You can also do that in your class. You're doing it already. So almost anyone can do that currently. Engineers trained, even undergraduate. I went to Mahidol University for a class lecture. Third year students, fourth year students are able to do this. So it's now pretty much okay, the first part. The second part is the analysis nonlinear model for real building. This is a big step ahead, and you can learn it because now guidelines are available, videos are available. There are books on that. Software have made it easy to do this one. That is still possible. It's a step up. The biggest challenge is that you need to now incorporate the actual reinforcement from the building drawings. So it's no longer that you just put the section, you have to put all the reinforcement in the model. And that takes a lot of effort to get that information. So design has to be complete, detailing has to be complete, then you bring it back to the model. It's just a lot of work, not so difficult. Next one's becoming more difficult then. Extraction of the results from the nonlinear analysis, because this can produce up to 1 terabyte, 2 terabyte of results. Terabytes, not gigabytes. I'm talking about terabytes of data. So if you have that much of data, just opening that data, getting the results back, compiling it, processing it, it's a huge task. And once again, even if you can do that, then finally understanding it. And that's where most of the difficulty lies, not in the first two parts. Okay? And that's what takes time, years of practice to do the third and fourth, right? Sometimes now it's getting better, but sometimes you have to wait days and days before this can just get the results, extracting the results, not running the analysis. That can take so much time because you have 11 ground motions. You have analysis. Every time step in a one ground motion runs for, let's say, 50 seconds, 1,000 time steps. So you have 1,000 results from 11 ground motions, 11,000 results for every column, every beam, and then all the load combination. So the results are just unbelievably huge. And then getting them, understanding them, averaging them, plotting them, it takes a lot of time and effort and understanding. So from that, then we move to, so I've talked about that. The questions from PBD, once we have done the PBD, as I told you, you can get a good idea of what the building, how the building will respond. But it doesn't tell you what is the risk and what are the consequences of, we are just doing a process, we say, okay, I'm here. But the question is, what is the risk of things not going as we predicted? Because this is not absolute certainty. Okay? It's still a gray area in many ways because you did a model, the actual material, so many things that are still not absolutely certain. So there is a still element of risk there, uncertainty there. So what if the performance level is not achieved in reality? That is the question then, that, okay, we have estimated everything, but what if that is not actually achieved in real building because of modeling inaccuracies, because of we could not model the foundation properly, maybe the material strength is more or less, or some member, put some extra mass there, some walls were added, because we can't know the structure all the time until it is there. So there's still a risk that this performance objective will not be met. And the risk you have seen in that building that I showed you earlier, the cracking, that's the risk that people have to take. Then what are the consequences of that cracking? What it will affect the people's life, it will hurt somebody, it will cause, people will lose their life savings that in their apartments or whatever. So the consequence of that risk are very different from PBD. PBD doesn't go into that direction, doesn't care what happens after that. Okay. And then what if the performance levels are not sufficient? Like I said, the baby hospital needs something more because they installed it. It's special equipment that cannot sustain even that much, like MRI, something like that. Or now all these data centers, extremely sensitive, right? So we don't even know what kind of performance levels we need for them. So these are the few questions. And like I said earlier, is this acceptable? Obviously, you will say not, but the courts say, yes, this is what you be designed for. Try explaining that to the tenants, that I designed your building for the code and you have to accept it. And that is our challenge. We are very lucky in Bangkok that the damage is there, but people are still understanding. And this is overall. I went to city. I talked to many people. There was a big event we had, and people start to know. Okay, there are people called structural engineers, and there are people who did some good jobs so the whole city survived because everybody felt the shaking, and 99.9999% buildings survived very well. So which means people believe that, okay, there's some engineering behind it which saved them because they saw one building collapsing. So it is a reminder that things can be that bad, but it wasn't that bad in your building. So you should be kind of thanking the engineers. So we are in a good shape right now at the moment, okay, in the public opinion. So we should be glad. But this is not good, as you can see from here. In public's eye, this is not good. And that is where, so even if we do the PBD and everything, we still get that. So now we have actually experienced it, so it makes it more real. You people haven't. People in tall buildings in Bangkok, you should ask them what happened to them. So this happens in so many buildings. The ceilings fall down, the partitions crack, and so which means the public and society still doesn't really accept our things yet, right? It's just like the development of the automobiles. If you look at the movies and something early, even in US, nobody's wearing seat belts. There's no top, people fly, because safety wasn't, it was acceptable to get hurt. People expect to get hurt in a car accident. Now, people do not expect to get hurt. They expect the airbags everywhere. They want the sensors. And they expect, and that is happening. Even in major accidents, people survive without any, most of the time. I don't know if you know that story about the Tesla car and somebody tried to drive it off the cliff. Do you know about that? Okay. So in US, there was one family, and the main, the person was driving. He decided to commit suicide by driving the car off the cliff with his family for whatever reasons. So when they tried to turn, the car won't let him turn because it sensed that it kind of bit. Anyway, he forced the car, but because the car already knew it's going to happen, so it engaged all of the safety features, the airbags, the seat belts, and everything. So even the car went down and hit, people were saved. But that guy was arrested by the police because the data went back from the Tesla, everything was recorded. And it was clearly showing that he intentionally drove off. But people survived because the car took the action before it could actually hit the ground. Everything was secure. And one of my friends, also in US, also driving a Tesla, and I saw that script. So he was coming and then turning right to go to his house. And then another car was coming, young person, whatever, drunk, whatever. And didn't see or didn't stop. And then when it was turning, it was coming straight and hit the car. And the car flipped over several times. But he was completely unhurt, completely. And then later, they have the script from the Tesla, and then the Tesla recorded that the impact is imminent, cannot be avoided. And I am taking the following actions. I'm tightening the seatbelts, I'm deploying the airbags, and I'm doing this. So the whole script was written down, and he was completely safe. My point is that other people are doing something about safety of the people as expected. We are still far from that. Okay? And that's why I think as engineers, we have to move forward because now we are getting the tools. Okay. Another one, last one, insurance. These are the guys that really look at that. Who is the most worried person in Bangkok right now? Insurance companies, because they have to pay for all this damage. Right? Last time was flood in 2012. You don't know about that, right? Yeah. So we had flood in AIT. Water was up to 2.5 meters, standing here for 2 months. Everything was completely submerged for we had to come to with the boats because everything was completely damaged. Somehow, lucky for AIT, just 1 year before that, somebody thought of doing flood insurance, which normally people don't do. So AIT got about 400 million baht after the flood. But my point is the insurance companies were not happy. And this earthquake, insurance companies are obviously not happy. So they really want this research to be done so they can then protect their value and they can insure the buildings properly. So the people behind the non-structural damage assessment funding is insurance companies. It is in their interest to do this, right? So if you want funding at this point, go talk to insurance companies for your research. So consequence-based. So it's not enough to say that cracking and non-structural damage is acceptable as long as structure does not collapse. This is our statement right now as engineers. It is not acceptable by the public, by the insurance companies, by the other people anymore. Just to say that, oh, my structure is safe, I don't care about the non-structural damage. It's not going to be acceptable, even more so. Then a natural extension of the performance-based design is that we have to go to do the, what they say, DDD, dollars, death, and downtime, triple D. You have to care about the money, you have to care about the casualty, and you have to care about how long the building will not be operational. So those 3 Ds are very important in dollars terms. Okay? So you have to be able to assess that as part of your design. What is the expectation of the damage? What is the expectation of the deaths? What is the expectation of the downtime for repair? That should be part of your design evaluation. Okay, that's what we are talking today. So all of this, lucky for us, can be determined from the analysis. We just have to go one more step beyond that. Okay, it's not that it cannot be done. It can be done. Frameworks are available, tools are available to do that. Okay. So the thing is that for risk-based design, now we need probability, risk, safety of critical element, design accidental loads, and then finally structure design. That means we have to think a little bit differently. First of all, probability has to come in. What is the probability? Already seismic design is probability. MC is 2%. Design basis is 10%. MC 2% means that 2% probability that earthquake will hit during the life of the structure. Design basis earthquake is 10% probability that it will hit that site in the life of the structure. Service level earthquake is 50% probability that it will have. So it was service level earthquake should hit 1 or 2 times. And so this earthquake that hit was between service and DB, wasn't MC. It was 1/3 of DB roughly. So it was not that we even reached the design level, which was below that still. Okay. So the point is that we have to do more probability of the consequences and then risk, quantify the risk. What happens? What is the value of the risk that I'm taking? Is it acceptable risk or not? Calculated risk. So calculate the risk. Then safety of critical elements. Then go back and say, okay, even though the PBD is okay, but this element is too critical, I will further add more safety and reduce the risk further by focusing on the shear wall. For example, that building, once again, if a risk assessment would have been done, the core walls should not have gone down like that. It's impossible in any scenario for the core walls not to keep the building stable. Everything else can go, not core walls. So somehow they didn't do enough. Stories are flying all over. They just reduce the thickness, whatever. I don't want to go into that. The point is that critical elements must be further enhanced to reduce that kind of risk. Okay. Then design for accidental loads. Also add some accidental loads that are not part of the typical to further eliminate the risk, reduce the risk, and then go for the structural design. So that's the procedure. We add 2 more levels before we do the design. Then we have to do this kind of site-specific consequence of failure and likelihood of failure. So these 3 things are very important now, which is beyond PVD, beyond code. First of all, site seismic hazard study, which is part of PVD. That means you cannot take the map from the code. It's meaningless. You have to do the actual assessment of the hazard at the site, studying all the faults as far as possible. So when we do the seismic hazard assessment of site in Bangkok, we take all of the faults in Myanmar, in China, in Chiang Mai, in Indonesia, all into account, not just in Thailand, because earthquake doesn't know boundaries, right? It's just, so we have to go as far as you can and then assess their impact on the site. Okay. Then okay, fine, this is what I want. Then consequence of failure, that, okay, what can happen if the failure happens? What are the consequences? Are they acceptable or not? Some are acceptable, some are not acceptable. You have to list this consequence, this failure, this consequence not acceptable, right? Go back to the risk. And then likelihood of failure, vulnerability. Okay. So all these things also need to be combined. Now, this is a very important graph. Acceptable risk limit. We say that expected consequences and probability of the hazard. One side, we have the probability of hazard, and the other side, we have the expected consequences. So very low probability and consequences also low is no problem. There's a low probability, you don't need to worry about that. And when you cross this point, very high hazard probability and expected consequence also very high in this region, you have to worry about those things. So you categorize the beams and columns and walls and whatever into this kind of a table or this kind of a, and then you say, okay, this one I don't need to worry. Let me worry about this. Something which can happen with the high probability, but the consequence is very high. I must prevent that, right? So you have to study both. Even if it's a high probability, but the consequence is very little, no need to worry. So that's the thing that we need to estimate or study, that okay, very high probability and very high consequence, critical. We must not let it happen. Even for low probability, but the consequence is high, we still should worry about that, right? So that's the idea of this whole diagram, to understand every consequence, plot them against their consequence, every failure against the consequence, against the probability of happening and the hazard. Okay? And that brings us to consequence and risk-based design, the next level. Few people do this at the moment, but people are doing it. As usual, we had one thesis done on that, and then it was quite interesting to find we finished the PVD and let's say, okay, let's do the risk. But for risk, you have to do more, not just one time with varying strengths, because right now we are just saying PVD is this structure, this hazard. But for risk, you need to vary the concrete strengths. You need to vary the probability of not meeting the expectation, some element not there. So you have to vary many things and study it and try to fit that. Okay? So you cannot just base it on one analysis. That's why it's so hard, because you need to work on the probability by varying the possibility of failure. Okay? So that actually brings us to a fragility curve, which I will show you in a minute. So So look at the overall impact much beyond the building. Now we have to go beyond the risk-based design. So risk-based design is only for the building. But let's say if it's a hospital or a fire station, if that hospital or fire station is damaged, the effect will be on the whole community. So it's now goes beyond the building. It's no longer up to the building. So resilience of the city or the community depends on that building. So the risk is not limited here. We need to go out and look at the impact. I remember when we started PVD, like early 20 years or something like that, we got some projects in Bangladesh to evaluate the fire stations. That was the first project because they were worried that fire station should not get damaged. And we started doing the nonlinear evaluation of the fire stations at that time, put some BRBs there. So immediately fire station comes to mind that, okay, they have to remain operational. So resilience-based infrastructure. So resilience is much more than engineering. It's very broad. It's the reliability, fast recovery, lower consequences. That's one block. And then you have the economic, social, organizational, technical. Then how fast, how redundant, how resolved. So resilience have big picture. I cannot go into a lot of detail, but the point is you have to think about everything. Will they have the money to do it? Do they have the people to do it? And this is what is going to be a problem or becomes a problem. Even though you estimate that your building will be repaired within a few months, but in reality, if there are 100 buildings damaged, you won't have the people. You don't have the material. You won't have the contractor. You won't have the designers. So it means the whole thing becomes meaningless. That's where the resilience comes in. And I have seen this firsthand in Nepal. So after the 2015 earthquake, we got a project from JICA and ADB. I was representing ADB, another team from JICA. We got $200 million to go there and fix up the schools after the earthquake. The money is with us, lying in the bank. For 1.5 years, we could not spend even $1 because the capacity isn't there to design. The capacity isn't there for contractors to bring the material. It was so sad that the money is there. Consultants are there. We were there. I was there for a long time. And we just couldn't spend any money for 1 year, more than 1.5 years. I think more than 1.5 years before the first school was built. By that time, they had already moved on, and then they make some makeshift arrangement, set the things up. Schools are going on, right? So that's the resilience of the community, that they just continued on their own without waiting for other things to come. So that's the overall resilience, big picture. In Christchurch in New Zealand, one earthquake happened. I forgot the year, 80s something. It took them 10 years to get back to full capacity. Several $billion, even though Christchurch, New Zealand has one of the best codes in the world. No building collapsed, but there was non-structural damage, some damage here and there. But the city took 10 years to fully go back to operation before the earthquake, right? So its resilience is a big picture of the city. So economic losses, loss of quality of life, loss of community and culture, everything can shut down. We have, an earthquake, because we went through this. I was going through the whole city on that day when earthquake happened. I could see everywhere the impact, people leaving the offices, standing on the outside. And then people cannot find the conveyance to go home. They cannot buy the food. It's not even a disaster yet. But you could see the city come to a standstill and how it affected everybody's life, at least for a few days. People are sleeping in the parks, that kind of thing. So you can imagine that if it's a real major event, then it will be all of that happening. So we have to take a big approach to the holistic approach on the seismic risk, not just what we are doing now, because we are the center where everything will start. Of course, water supply, communications are also part of that, but they're all attached to the building. So the water supply actually broke in many buildings because of the drift. So this is what they're doing. Green Building Initiative was started long time ago to make them environmentally green, right? And then another was started, resilience building. So you have the United States Green Building Council, and they say, okay, we want United States Resiliency Council to match with that. So these now go together. Sustainability, resilience combined together to complete the big picture. So they followed each other and connect to each other, right? So this Resiliency Council, Resilient Buildings, is an initiative to make the buildings resilient the same way as they make the buildings green. So we should have it like green building have a rating, right? Gold rating, silver rating, platinum. We don't have resilience rating yet. And there's a big danger in that, because if the building is not high resilient, people will not buy it. People will not live in it. Unlike the green building, which is not the same. So resilience is not being applied because nobody wants to put a bad sticker on the building. They won't be able to sell it, right? Anything less than gold and platinum, people say, why should I live here if it doesn't have a good rating? So this READY initiative, about 10, 15 years ago, they started Arab, Arab is the world's largest consulting firm. So they started this initiative, and then other people joined in. I used to attend their meetings at that time. Okay, so they have these ratings: platinum, gold, and silver. And this is their framework. If it is a platinum building, platinum rated building, immediate reoccupancy, earthquake finish, you go back. Building has no damage, nothing, right? Then direct financial costs, less than 0.2-0.5% of the building costs. And then physical injury to failure of building, completely unlikely, nothing. That is the one gold standard, platinum standard, that you should have the building. Right? Next one is gold, immediate recovery and all of that. Scenario expected loss 5%, some injury, little bit. Silver, 6 months to come back, right? If everything is available, 10% loss, and some people got hurt and things collapsed, right? So who will live in a silver building? Even that is not achievable in reality. Code-based design doesn't even come close to them. So that's the problem. Here you are. So this is the platinum building. Platinum building, within 3 days or less than 3 days, go to 100% functionality. This is the time versus the level, except, professional level, confidence level. So platinum building is supposed to go back fully. Nothing happened to it. The gold is go to books, and code is here, that red one. So if the building is designed for code, like the one I showed you in Nepal, you expect it to get damaged and not fully recoverable even after 2 years with a lot of cost. That's the code level. And if you show this to the public, they will say, why are you even designing our buildings if you expect this already to occur? But then you say, okay, if you want it to be platinum, you have to spend a lot of money. Once again, they will not have the money to do this one. So it's a balance between that initial cost versus the risk. If somebody has the money, like platinum, green building also costs a lot in the beginning, but they save over time. Similarly, platinum resilient building costs a lot in the beginning, but you save in case something happens. So that's the trade-off between initial and later costs. And then we have all this prescriptive requirements and ready guidelines and all of that stuff. Backup system for everything. So then code, design demands, we have to also consider vertical earthquake, minimum structural damage, minimum drift, expose the structural elements to inspection, and then we have to do a systematic design. So there are many things that they want to do. I don't want to go into detail. Let me show you this thesis that I mentioned to you was done by Catherine Diaz, enhancing seismic resilience of non-structural measures for tall buildings in Manila, Philippines. So this is what she did. She took the building in Philippines, do the design, code-based design, then do the PBD, fixed everything, then she evaluate the resilience, then she go back and improve the resilience. Okay? So complete the whole cycle. And she did a good job on that one. Yep. So this is some of the things from her. So she did that, so she collected the data. You need data now. You need to know how many people are going to live in each room, what partition wall is used, what is the ceiling, what is the door, what is equipment there. You need all that data now to come to you, first of all. Then structural analysis, whatever software used, then define components, loss assessment, then determine level of resiliency, enhance the component, determine cost for enhancement, and go back to do it again. So it is possible to do it, right? You do that, but you need data. So that was our first objective, and that was our second objective and third objective. To first of all, just do this loss assessment, then enhance, and then reevaluate, right? 3 steps. So it's also giving you some idea about your thesis, how theses are organized in this way. Somebody can continue this one, because now what we are thinking is that we should now, at that time, there's no BIM. Now BIM is everywhere. So why can't we bring in the whole building from the architectural BIM together and just do on that, because BIM has all the information, right? So we connect this resilience to the BIM model and redo this thesis again. Anyway, so now this is important. This one is the design basis story drift. So we plot the drift along the height. And then we also look at the drift sensitive components. So in the building, there are 3 types of damage can occur. Because of the drift, things can crack like partition walls and so on. Because of the acceleration, ceiling especially are damaged because of the acceleration. And then because of the velocity, which is mostly damaging the mechanical equipment and electrical stuff. They are sensitive to velocity more than acceleration. So you need to categorize which components will be checked for drift, which component will be sensitive to velocity, and which component sensitive to acceleration. Then you determine the drift, acceleration, and velocity and acceleration at each floor level. And then you find what is on that floor level. And then from there, you can assess the damage using what is called fragility curves. So fragility curves are curves people have drawn from testing those things against the drift levels. What is the damage expected? So that's another challenge, how to get the fragility curves for every material, because you have to test them under various damage conditions. And this is for the peak floor acceleration and acceleration component damaged because of that. So you can see which component will be damaged, how much on each floor. And from there, you can estimate what will be the total damage, which floor is more critical, which floor is not accessible, where the where ceiling will fall down, where the walls will crack, where the water supply will break, and so on. So you can assess all of those things from this analysis, going one more step after that, calculating drift, which we already have, acceleration, and velocity, and then connect it to the building components. And then you can go back and draw your own curve for that building. And then you can say, okay, this is where I want to be. I can bring it back. And then let's say in the beginning you are here, you fix it and you can bring it back. You can reduce the time of downtime and cost, right? Then you can tell the owner, if you spend more now, or you change this to this one, it might be better for you. Owner may or may not listen, because sometimes they don't care. They sell the building, they're gone home. So they don't care what happens to the tenants, right? But some owners will care, because if they are data centers or hospitals or something like that, they would care. So that's these are the components. So mostly it is about the details, how you connect things to the structure. If you provide enough movement gaps and allow the structure to move while the non-structural components are kept isolated, you can save them. So mostly is about improving the details. Here, for example, the walls should not go and connect. The ceiling should have a, it's kind of a gap, movement gap, and other things also. So everything is about details. How you connect the non-structural components to the structural components to prevent them from being damaged and not accelerating, not drifting, and so on. So it's all about the details and making sure that those details are followed. Most of the building, the glass did not break because they have a gap. When they fix the glass, there's a rubber gasket around that, which provides that small movement allowance. The facade panels did not fall down in most buildings, even though the building shook a lot, right? As much as 1 meter. Some buildings moved more than a meter, right? But because they are designed with a little bit of gap. So it's all about, like I said, detailing, how to improve the detailing, hang something, put the wires. So it comes down to how you fix the non-structural things to the structure. And if those details are well done, then you can save the non-structural things from that. There you can move it. See? So this is the no rating code level. If you're here and if you want to go to the rating, you improve everything, you can bring it back to that level, okay? From 1.5 years to 3 months or whatever. So that's the advantage of resilience-based design. After you check, you fix, you can prove that, okay, this is the benefit that you're going to get. So now silver rating only. She was only able to get silver rating for her building. So that's the whole idea, save the people from all these hazards, ultimately.